notation using the Greek letter sigma. So we said this is the uppercase Greek letter sigma, and we use it as a notation for sum. So there's an index, we said, that I runs from 1 up to some number n, and we agreed that this number could start at any, but especially in statistics we start at 1 and we finish, let's say, at 4 or at 5. And let's look at this example from let's say now the index is x sub I. So this means it's basically the same as x sub 1, so I is the first term, and then plus x sub 2, plus x sub 3, and then of course the last term in this case is x sub 4. Now we'll extend this idea to see what happens if we multiply this x by a constant, or if we subtract a constant, add, what happens. So let's, for this example, what we're going to do is, let's make it a practical example. So let's say x1 is 2, okay? The first term is 2, and the value of the second term, let's say x2 is, let's say, 4, right? And then the third term, let's say x sub 3 is 1. So let's look at this example now. So what would be the value of this notation here? By the way, sometimes we don't see even the index I is equal to 1 up to something. If it's very clear, we just only see the summation notation. And for this one, let's close this off, right? That's for the first example. What about now if we wanted to add from 1 up to 3 of these numbers, 1, 4, and 1. But now instead of just adding x, now we'll just multiply it by a constant. So let's say 5 times xi. So what's the value of this expression now? Sigma I goes from 1 to 3 of 5 times xi. Well, again, because we're using the order of operation, 5 times xi basically means the first term will be 5 times x sub 1, and then the second term will be 5 times x sub 2, and then the last term will be 5 times x sub 3. Sorry, it should be sub 2, second term. So the second term is 5 times x sub 2, and then the last one is 5 times x sub 3. So basically what we're adding now is that if you multiply the indexed variable xi by a constant, you just continue to do the same thing. So now the term is now 5 times xi. So in our case, because the first number is 2, so this will be 5 times the value of x sub 1, which is 2, right? And then plus 5 times x sub 2, which is 4, and then plus 5 times x sub 3, which is 1. And using our order of operations, before we do addition, we multiply. So 5 times 2 is 10, and then plus, again, before we add, we multiply. 5 times 4 is 20, and then we do the same with the last one, which is 5 times 1 is 5. Now when you add these numbers, 10 and 20 is 30, and then we add 5, the last term, and of course 30 plus 5 is 35. All right, so this gives us a summation notation when we multiply the index variable x by 5. All right, now let's look at another example where we would be able to find the value of I may have to erase this part. Okay, so we'll use the same so let's erase this part so we can reuse this. One more example where would have subtraction and addition and even exponents. So let's do just one that will do most of it. So now evaluate the value of the same. Now I goes from 1 to 3, right? I goes 1 from 1 to 3. Now instead of we just did 5xi. So what about now if you wanted to do first subtract, let's say 1 from each xi, and then square them, right? So now notice that what we're doing here is that only xi is the one that is indexed. So x1, x2, x3, so there would be 3 terms here because xi runs from 1 to 3. But the -1 and the 2, they're constants, so they will remain the same. So the first term here would be x sub 1, right, minus 1 quantity squared, right, plus, now the second term is x sub 2 minus 1, again quantity squared, and the last term is x sub 3 minus 1 and then quantity squared. All right, I'm going to erase the bottom part as we continue to do this example. So in this example, in the second example, we'll do pretty much the same thing that we did in the first example with that additional operations of subtracting 1 from each value of xi and then also simplifying it later. So I think for our purpose, let me use a different color here. So if we were using, let's say, a blue color here, this part right here is the one that is being added from 1 to 3. But then within that term, each term for the I is 1, I is 2, I is 3, that's the only thing that is indexed as I. So this is not 1 times xi, so it doesn't have the index, so it remains constant. So if we continue now with this, so this will be is equal to, right? Now, well, x1 from this example is 2. So we have 2 minus 1 squared, right? Plus, so even though, you know, sigma is good for summation, which is what these two are coming, the sum, these two sums are coming because of the sigma notation. But inside the term, there's subtraction in square, right? And then the second term is 4, x sub 2 is 4 right here. And then minus 1 squared. And the last term is 1 minus 1 squared. Again, the sum is done the last, and when it comes to order of operations, we'll do parentheses first and then exponents, and then we'll do add. So 2 minus 1 is 1, and then we'll square it, and then plus. Again, inside the parentheses, 4 minus 1 is 3, and then we'll square it. And then the last term, 1 minus 1 is 0, and we'll square it. Still, we can't do addition. We have to do exponents first. Even though this example is about the sigma notation, we still have to follow the standard order of operations. So 1 square is 1 plus 3 square is 9 plus 0 square is 0. And now we have 1 plus 9 plus 0, which is 10. So the value of this expression, sigma I goes 1 from 2 3 of x sub I minus 1 squared is 10. So this is just only introducing how to use the sigma notation. Later on, we will come across formulas in statistics, especially, where when we find the mean, the standard deviation, the correlation coefficient, then we'll be using this sigma notation, and I hope you'll find this to be helpful. Okay.